Our final lesson in topic 6b has us using exponential functions as a means to describe sequences and series. We worked with arithmetic sequences back in topic 1. Today we'll focus on what's called geometric. We'll first recall some of the information from arithmetic sequences back in topic 1. So think about something like 5, 7, 9, 11, and so on. We would call this arithmetic because we're adding 2 each time. And what we were able to do with that information is write formulas to generate any number within that sequence. We could also create it as a series and find the sum. A little bit of review. An arithmetic sequence is going to be something that requires the first term and the common difference. If you know those two definitions, the formula for any formula in an arithmetic sequence is a sub 1 plus d times n minus 1. That was called the explicit formula. Whoops. Once we knew that formula, we could find any number within that sequence. Another way to write an arithmetic formula is called a recursive sequence. This is where we had to split it up into two parts. We wrote it out as a sub n equals, and then we did that bracket on the left-hand side. A sub 1 was always the first number, and that was when n equaled 1. That's an n right there. And then it was a sub n minus 1. Wow, that's hard to see that right there. Sorry. That says a sub n minus 1. Let's get that to be written a little bit better. There we go. Plus d, and that was for anything greater than 1, any n value. That just meant we kept adding d to the previous number. To find the sum for an arithmetic series is simply when we just added all the terms together. So 5 plus 7 plus 9 plus and so on. And then to find the sum, I don't know if you guys remember this fun formula, S sub n equals n times a1 plus an, all divided by 2. Do those formulas sound familiar? We're not going to use those formulas specifically in this lesson, but we are going to generate new formulas for new types of sequences. The formal definition for a geometric sequence is going to be a sequence with a constant ratio between consecutive terms. What that means is you're multiplying to get the numbers within that sequence. Now, you can multiply by a whole number or a fraction, and you can multiply by a positive number or a negative number. To determine that constant ratio, you always take a term in the sequence divided by the one that comes right before it. Here are a couple of ways to do that. To figure out the ratio, you could take the second term divided by the first term, or the third term divided by the second term, or the fourth term divided by the third term, and so on. If those numbers are consistent, then you have a geometric sequence. For example A, determine if the sequence is arithmetic, meaning we're just adding, geometric, or neither. It goes 2, 4, 8, 16. If we're trying to figure out if this is geometric, we would do the second term divided by the first term. We would do the third term divided by the third term divided by the second term. The fourth term divided by the third term. Notice our R value, the ratio is the same each time. That means this is geometric. And the pattern is we're multiplying by 2 each time. That would be that common ratio. Let's try the next one. 2, 4, 6, 8, 10. Well, it looks pretty easy to tell that we're adding 2 each time, which would make us think initially arithmetic. But let's check to make sure it's not geometric as well. To figure out if it's geometric, we do the second term divided by the first term. And notice we get 2 again. But now watch what happens when we take the third term divided by the second term. We get 1.5. So not the same as that first common ratio definition. Therefore, it's not geometric, it's only arithmetic. And we're adding 2 each time. Okay, let's try the next one. 1, 4, 9, 16. Well, right away, we're not adding the same thing each time, so it's definitely not arithmetic. To be geometric, we check that common ratio for the second term divided by the first term. And then we take the third term divided by the second term. It's definitely not geometric either. The ratios don't match up. This means it's a pattern that's neither arithmetic or geometric. Do you recognize anything about these numbers? There is a pattern to them. They're all perfect squares. Okay, that's kind of fun, something different. Let's try one more. 99, 33, 11, and then 11 thirds. Oh goodness, okay. Let's take a look here. It doesn't look like we're subtracting the same thing each time, so the pattern isn't arithmetic. Let's test and see if we have a geometric pattern here. To get our ratio, we'll take the second term divided by the first term. 33 over 99 reduces down to 1/3. If we take the third term divided by the second term, that also reduces to 1/3. Ooh, this one's kind of tricky. 11 thirds divided by 11. Well, instead of dividing by 11, we would multiply the fraction on top by the reciprocal. That would be 1 over 11. Ooh, the 11s cancel, and we do in fact get 1/3 again. This is an example of a geometric sequence. We're multiplying by 1/3 each time. Our ratio can be a whole number or a fraction. It can be positive or it can be negative. A formula used to generate any geometric sequence can be written in one of two ways. We have explicit, and then down below we have recursive. The explicit formula follows this template. A sub n equals a sub 1 times r to the n minus 1 power. Notice this is an exponential function, and this applies for all values of n greater than or equal to 1. A sub 1 is the first term in that geometric sequence, and r is that common ratio. What are we multiplying by each time? Let's put this to the test. Write the explicit definition for the geometric sequence 6, 18, 54, 162. Verify the first 4 terms. Well, I recognize right away that the first term is 6. To figure out our r value, we take the second term divided by the first term. Take the third term divided by the second term. 54 divided by 18 is in fact 3. Try that last one. 162 divided by 54, also 3. That's our r value. Once you know both of those numbers, the explicit definition is really straightforward. A sub n equals 6 times 3 to the n minus 1 power. And this is true for all values of n greater than or equal to 1. Oops, there's a 1 right there. There we go. Let's test out those first 4 terms. A sub 1, that means it'd be 6 times 3 to the 1 minus 1. 1 minus 1 is 0. 3 to the 0 power is 1. And 6 times 1 is 6. To get our second term, we plug in 2 for n, and just keep going. Simplify from there. 2 minus 1 is 1. 6 times 3 to the first power is 18. And you can keep going to verify the rest of the terms by plugging in your value for n and simplifying. The recursive formula, or the definition for a geometric sequence, incorporates the a sub 1 value and that common ratio. It's just written in a different format. We write this as a sub n equals, and then we have that breakdown. A sub 1 when n equals 1, and then we have a sub n minus 1 times r. And those are for values that are greater than 1. Let's use that template to rewrite the formula in example 2a as a recursive definition. We have all the parts we need, therefore we're just going to write a sub n equals, and we do that big bracket. A sub 1 means the first term, and the first term in that geometric sequence was 6, and that's when n equals 1. To get anything after that, you take the previous answer, which would have been 6, and we multiply it by our r value. And in this case, our r value is 3. Those are for values of n that are greater than 1. And that's all we do. That would be the recursive formula for that geometric sequence. Here's our final example for today. Is the sequence 12, 9.6, 7.68, 6.1344 and 144 and so on a geometric sequence? If so, write the recursive definition. To test if something's geometric, we go back to that r value like we did before. Take the second term divided by the first term. If we take 9.6 divided by 12, we get 0.8. That's the second term divided by the first term. Now let's go to the next pair. The third term divided by the second term. If you plug that into your calculator, you also get 0.8. Try the last one. 6.144 divided by 7.68, and you get a match 0.8. That is our r value. If the r value stays the same, then yes, we have a geometric sequence. Now write the recursive definition. We know a sub 1, that's 12. That was given to us in the word problem. We know our r value, that's 0.8. We calculated it. That's all you need for the recursive definition. A sub n equals, and then we have that big bracket. A sub 1, which is 12, and that's when n equals 1. Then we take a sub n minus 1 times 0.8. Those are for all the values of n greater than 1. And these are your notes for the first half of 6.7, day 1. Make sure you have all of these written down and then complete your short Pearson 6.7, day 1 assignment.